Hello, everyone. My name is Pavel. I will try to enlighten you about flat maps, what it is, what it isn't maybe, when to use them, when not to use them, and the general idea of how they work. So I hope you will learn from this talk, or rather I will try to remind you about standard associative containers and when to use them. We'll talk about what is flat map. We'll talk about a little bit about boost flat map implementation and STD flat map proposal that I believe is in C++23. We'll look a bit on at performance comparison between different implementations and different containers, and we'll look at what else can we do or could we do with the flat map to make it more usable and convenient. Okay, let's go. So here are three basic standard containers that you should consider in the order of priority. So the first container that you should consider when you need a collection, you should look at vector. Then if you need an associative collection or associative container, you need to look at an ordered map. And finally, if you need associative container and you need elements to be ordered, you should look at STD map. So I would ask you to tell me what guarantees does vector have if we consider the first element of the pair a key, and try to answer it and compare to what answer I would expect from you. So what we want to talk about is guarantees about keys and elements. And I would expect you to answer eventually that keys, so to speak, if we consider the first element keys, are not unique. And so there is no guarantee about uniqueness. And there is no guarantee about order. So the keys or elements with keys, so to speak, are unordered. I hope you will answer the same question for unordered map. So which guarantees does it give us for keys and for elements? And I hope you answered like this. Unordered map gives us a guarantee that all keys are unique and elements are unordered. So there is no guarantee about the order of elements. And the next question is about STD map. And the question is the same. What guarantees does STD map give us? And I hope you answer to yourself the same as I would expect, that STD map gives us guarantees about keys, that they are unique, and guarantees that when we iterate elements of the STD map, the elements will be in order. So let's talk about flat map a little bit. Flat map gives us the same guarantees as STD map, and the difference between them is in the implementation. We'll get to that. Let's recap basic knowledge about standard containers. In this case, you see STD vector example was STD vector, and vector allocates one chunk of memory and stores every element contiguously in the memory, and possibly has some capacity, unused memory to store elements that you will add subsequently. Complexities of the operations are predicted as linear or search, insertion, removal, and we have a special case that if you add elements at the end using pushback, the complexity is amortized constant. So next is unordered map. To use unordered map, you have to specify hash function or hash functor, and you have to specify equality comparison. So in this case, the default types are std hash and std equal to, parameterized with key. For each element, basically, for each element, memory allocated to store it within a node. So basically, for each element, we have a memory allocation. Nodes are organized into buckets, depending on the hash value of the elements or the keys in this case. And so we have complexity guarantees that an ordered map can search and insert and remove elements in constant time on average. The next one is, oops, sorry. My remote broke. Let's use mouse. Okay. So yes, the next one is std map. And to use std map, you have to specify less comparison or order comparison. In this case, by default, it is std less. Again, for each element, a node, a memory for a node is allocated, and the element is stored within the node. And usually the nodes are organized into a search tree, and we have complexity guarantees for search and element insertion and removal, logarithmic. So flat map usually adapts a vector-like container. So, and first of all, in order to use flat map, again, as in the case of std map, you have to specify ordering order comparison. In this case, by default, it is std-less, and as in the case of std map. Since we adapt a vector-like container, by default, we use std vector, and all the features we kind of inherit from vector. So for elements, it allocates one chunk of memory. It stores elements contiguously in that chunk of memory. Possibly it can have spare capacity for elements that you can add to the map subsequently. And complexity guarantees for flat map are for search logarithmic, and element insertion and removal is linear, like in the case of vector. So this implementation flat map kind of combines vector and std map. So let's implement basic flat map. So basic kind of version of flat map. In our case, it will be a class template. We have to have template parameter for key, for value, for comparison, and for container, sequence container. In this case, by default, it will be std vector from key value pair. The definition, you can see the definition. In this case, I decided to privately inherit from compare. In this case, I get possibly empty-base optimization. Typically, implementation use compressed pair for this reason. Next, you see our storage for container. And here is somewhat boring parts that we want to define to follow what the standard for containers is. In this case, we have LSS for key, for value. We have LSS for value type. In this case, it is a pair of const key and value. And we have LS for comparison. We have LS for reference. In this case, it is a pair of const reference to key and reference to value. And for const reference, it is a pair of const reference to key and const reference to value. By the way, I forgot to tell that please use Zoom Q&A facility to ask questions if you have questions. I will not be able, unfortunately, to look at Discord during the presentation. So let's go further. Here we have, unsurprisingly, aliases for size type and difference type. Here we have aliases for iterator and const iterator, in which case we adapt container iterator in using our iterator type that we'll get to later. For const iterator, respectively, we adapt container const iterator. And for reverse iterators, we adapt using reverse std reverse iterator, and const iterator, respectively. And finally, for container type alias, we have container. So to slightly more fun stuff, we have default constructor. We have size function, size method that basically translates the size of the internal container. We have begin functions that adapt iterators returned by container begin method. We have end methods that respectively adapt iterators returned by end iterator, container end iterator. And finally, we come to the meat of the implementation, so to speak. This is the find function. Here we want to return in iterator to an element with equivalent key or end if such element doesn't exist. So first of all, we have to get a predicate to search for the element. And we use that predicate to try to find the needle. So here's the implementation of find needle. Here we just wrap a lower bound call, not to repeat it all over the places. And this is just very basic usage of lower bound. I, of all places, found the most helpful to me description of what lower bound does in the comment in the sources of MSVC standard library, and it says that lower bound finds first element not before key. So what does it mean? The bottom, you can see that we have in our sequence some elements, a bunch of elements are the sequence is sorted, of course. So some elements are maybe before the key, so before. And there is some notion of an element that is not before the key. So we skip all the elements that are before the key as told to us by the predicate, and we return the next element. And here's the implementation of the predicate type. The most interesting part is comparison, implemented in the operator function call. We just call the comparison for the comparison of a key and value type of a container. We compare the key with the key inside of the element. And this is the same in reverse order. And this is the comparison of the keys of two elements inside the container. And so this is the function that constructs predicate for us. This is slideware. This is not production code. It has problems, but they are not important to this talk. Let's see if anyone finds the problems. So, okay, we got the predicate. We try to find the needle, and now we have to understand that if the needle is equal to the end iterator of the container, then we did not find a candidate with the equivalent key. Otherwise, if the needle is not equal to end iterator of the container, we check that whether the key is before the needle. So if that's true, we have needle is not before the key as guaranteed with eventually lower bound function that is called inside find needle. But we find out that key is before the needle, so we can get from that key and needle are not equivalent. Therefore, we can say that the element with equivalent key is not found, and we return end iterator. Otherwise, the needle is not before the key is not before the needle, as we can get from the comparison in the previous clause of if. And from that, we can get that key and needle equivalent, and we return the needle iterator adapted by our adapter iterator. For const version, we have this kind of trick. We constcast away constants of this, and we use mutable version of find. We get iterator from that. We then return that iterator, adapting it with const iterator type. So now we can take our find function and turn it into insert function. Here we have very similar scenario. We get the key from the value that we want to insert. We get the predicate. We get the. We try to find the needle. If the needle is not found, or rather, if an element with the equivalent key is not found, we insert the value that the user gave to us, and we return the resulting iterator, adapting with iterator ls, and we return true as the second member to indicate that we inserted the new value. Otherwise, if we found the needle with equivalent key, we just return that needle iterator adapting to iterator, and we return false to indicate that insertion did not happen. So to get version for R value, we just have to specify our parameters as parameter as R value reference, and we have to use move inside our insertion. Next, we can take our find function and turn it into subscription operator. Again, we get our predicate. We try to find the needle. If the element with the equivalent key is found, we place the new value in this strange, seemingly manner, because we want to adopt the behavior dictated by the standard for other containers, and we have to use piecewise construct of the pair type that you can see at the bottom of the slide. Otherwise, if we found already existing element with equivalent key, we just return the value as a reference. We have question. Would it not be cleaner to define find to operate on const at once and avoid the need to cast away the constants? You can do this, but that is undefined behavior asking to happen. I will get to that at the end of the talk if we have time. So I will answer that question in the Discord chat if we will not get to that. Okay? Okay. So now we can write a program like this. We can construct an instance of flat map, in this case, an empty instance of flat map, we can, using subscription operator, add an element. We can insert elements like this. We can insert a copy of an element like this using insert method, and we can try to use range4 to iterate over elements in the map. So let's see what the range4 turns into. And we can see that of all the needed operations, we did not define not equal for iterators, incrementation, and the reference for iterators. So let's do this now. Here's our struct type template. You can say which accepts key type, value type, and iterator type that we want to adapt as template parameters. We have we are storing an instance of the iterator that we are adapting. We have a constructor that moves the value of the iterator inside our storage. We have increment that just increments the initial iterator and just return itself. We have the reference that returns a pair of references to key value like this. And we ask the compiler to generate all kinds of comparisons for us because we just don't want to do this by hand. And so this type is used for our iterator and const iterator aliases, where we want to adapt container iterator and container const iterator respectively. So the problem, or rather nuance here, is that our dereference operation returns a pair of references. So when you write the code like at the bottom of the slide, the reference returns a pair, an object, temporary object of that is the pair of references, not a reference to some other object. And we do this because we define the container as a pair of non-const key and non-const value. But we define value type in our flat map as a pair of const key and whatever value. Because as in the case of standard containers, standard associative containers, we don't want to give the user opportunity to change the key and to ruin invariants that has to be established for our map to work. And so this is kind of messy, but this is the best way I came up with to kind of protect the user from itself, from himself or herself, and not allow them to change the key when you iterate over elements. So let's see how Boost FlatMap deals with this. And Boost FlatMap defines sequence, or rather iterator and const iterator type depths, like as iterator and const iterator of sequence type, just straight up. And we'd want to know what is the sequence type, but you just from that definition can't trivially or simply figure out what's the sequence type. So we can ask help from our IDE that in the pop-up note tells us what it is. And this is roughly Boost container from pair, or rather of pair of in value. So this is already looks not very well, because it ends up that our Boost flat map container has value type the same as the one in the vector. So in this case, it's non-const key. And when you dereference an iterator of such flat map, it returns a reference to the value type just straight up. This is kind of mess solution because it allows the user to change the value, or rather to change the key, and that way you can ruin the invariance that a flat map is looking for. So you can easily break the correctness of how flat map works. So theoretically, you can mitigate that by specifying const for k, but that has other downsides. We'll probably not get to that. And so in our flat map, we have by default the container of pair of non-const key value, but we want to have a value type or a notion of a value type of const key and value. And for that reason, we have no choice but to return from the dereference a pair of const reference and a reference to the a const reference to the key and a reference to the value. We have another question, I think. What would break if we tried to define the container as vector pair const key value? That's a great question. Unfortunately, it's out of the scope of this talk. I can't answer you from the top of my head. I will get to you in Discord. Please watch it. Yes. So, okay. Now, let's get back to our range 4. In this case, we specified reference as const. We want to iterate over const referred as, how do you say it? We want to iterate over elements with the const reference to them. So in this case, the reference of the begin iterator will, at the bottom of the slide, will return a temporary object, a pair of references. And this will work because temporary object can bind to const reference. But if we want to iterate over elements and to have non-const references to them in order to change them, we can specify simple reference, in this case, auto-reference, and eventually the reference will return temporary object, the pair of references, and temporary object cannot bind to non-const reference. And so similar situation arises when we want to iterate over zip view. In this case, the reference of the iterator of the zip view will return a tuple of references, and these temporary objects can bind to non-const reference. Fortunately, there is a recommendation to use value reference. In this case, not to type it out the actual type, we use auto-ref, and this will work in cases when you need to change values that you are iterating over. So in case of ZPU, this works. Temporary tuple with references will bind to a value reference, and it will structurally bind to A and B, and you will be able to modify A and B. And the same way it works with our case, in case of our iterators, the reference of the begin will return temporary object of references. The temporary object will bind to a value reference, and this will work great. So this is maybe not the way people are used to do it, but using that recommendation, it works. And maybe you have to exercise some discipline to be consistent in all cases when the reference is a actual reference, and when the reference is not an actual reference but temporary object, like in the case of ZPU or in the case of flat map iterator. So, okay, I think we are done with this. Now let's get to what is proposed to include in the C++ standard. I believe this proposal is accepted into C++23, proposal 0429 by Zach Lane. It proposes class template flat map like this, where we have to specify key, value, comparison, and what's different about this, and that we have to specify different containers for keys and for values. We'll get to that a little bit later. So let's look at some benchmarks. Here you can see the results for pushbacks, and you can see the times for the whole bunch of operations. So for one pushback, you can see time for one pushback. For 65,000 operations, you can see the time of all the 65,000 operations. This is not convenient to look at because we kind of see more or less clearly on the right side what happens, but we can't see very well what happens on the left side. So we'll see at times as averages over all the operations. So for one element, it's the timing of that one operation. For 65,000 operations, it's the average of all the 65,000 operations. And here you can clearly see that for a small number of elements, pushback is relatively slow, but this happens because for a small number of elements, there is a relatively large number of allocations, and allocations can't the cost of allocation can't amortize over several operations, and we have subsequently high cost for one operation. But as we look at the results for larger number of elements, you can see that the cost of allocations is offset by the number of operations. So for larger number of operations, you have fewer allocations, and that cost kind of spreads all over all the operations. And on average, one operation becomes cheaper. And in fact, it is predicted that, or guaranteed that, complexity of pushback is constant, and we kind of can see that for a larger number of elements as the cost of allocations spreads over them. So again, we are looking at averages. For lookup, let's look at lookup. For lookup, we can see that STD map is the slowest for large number of elements, and another map is the fastest for large number of elements. This is kind of not surprising for another map because it is guaranteed that on average, another map has constant complexity of insertions and removals, and also lookups. So I hope we got it. So we kind of it is hard to see what happens on the left side of the graph. So let's do. Before that, you can see that the horizontal axis is in log scale, and this doesn't reveal the logarithmic nature of lookups for maps, for other maps other than an ordered map, and if we change horizontal axis back to linear scale, you can kind of see that change in performance looks like logarithmic, like a logarithm. So I think we are done with the right part. Let's zoom in into the left part of the graph and see what happened there. So here we can see that nothing much is happening. We can say that all of the maps perform kind of similar for a very small number of elements and operations. And at some point, we can see that an ordered map becomes significantly faster than other maps. Again, this is predictable because of the difference of the complexity of the operations, and don't take the values like final values. This is just for illustration. It doesn't mean that this always happens this way. You have to measure things at your site, or at the hardware you are using, with the compiler you are using. These graphs are just for illustration. So from this illustration, we kind of can see that for small number of elements, they perform relatively the same. And at some point, maps other than an ordered map become slower. So let's look at insertions. We can see that flat maps become very, very slow for large number of elements. We kind of can't see what else happens because of the scale. So let's zoom the vertical axis. So we kind of zoom in this direction. And before that, of course, I forgot about that, to confirm the predictions or guarantees that the complexity is linear, we can change the horizontal axis to linear. And we kind of can see that all the changes of the performance, depending on the number of elements, look like lines, straight lines. So, okay, let's zoom in on the vertical axis, and we can see this. This is kind of mess. Let's try to untangle this mess. So the first thing that I can see is that flat maps are the fastest for a small number of elements. So in this case, boost flat map and flat map are the fastest among all the containers compared to at least to another map and map. Next thing is that STD flat map is roughly twice as slow for a very small number of elements because we have two separate containers for keys and values, and we have to do twice as much allocations when we add elements or remove, or rather, yes, only add elements. We probably don't have to do allocations when we remove elements. So, and you can compare that to the pale blue graph for pullback, and as influence of allocations becomes less important, the larger number of elements we look at, we can kind of see that STD flat map performance comes closer to the performance of other flat maps implementations. So people at the committee, at the standard committee, decided that that's a good idea to have two containers, two separate containers for keys and for values. Okay, I have no input in that, but I have to say that this is not composable in the sense that if you want to use one container, like with the boost flat map, you can do this, or you have to devise some crazy adapters to separate one container into two separate adapters that look at that one container. So it's crazy. And I think we'll touch this at the end of this talk. And so in the standard implementation, you have this type containers that contains physically separate keys and values separated into two physically different containers. And this collection of containers lives inside std flat map. So at this point, we can roughly outline when to use flat map, when can you use flat map, and I would suggest that you can use flat map when the maximum number of elements is constant and small. For example, if you have maximum 30 elements at all times, and this does not depend on the user input, so it cannot exceed these 30 elements, you can use flat maps. Otherwise, you can get into very, very bad performance, because for a large number of elements, performance of flat map is kind of suboptimal. And so my recommendation is use flat map for like certain elements or less. Other non traditional, I would say, cases can be to use flat map for mostly lookups when an ordered map is not available. So you can initialize flat map once. You don't have relocations in that case, and you only can do lookups. And the other case is when you want to mostly iterate over elements in the map, and you rarely insert and remove elements, and you want to iterate in order. So you ideally initialize your flat map once, and then you can very efficiently iterate over elements in that flat map because it's backed by vector, and vector has probably the most efficient iteration performance of all containers. So that's that. And of course, there is no universal solution or advice other than measure. So please do measure. Your mileage may vary. And now let's get to my most favorite feature of flat maps, and that is the ability to extract sequence. In this case, we get items from Boost flat map, and let's try to comprehend what type is that items container. And I slightly lied to you. In fact, it is not just boost vector of pair. It is boost vector of pair and using boost container new allocator of pair. So, okay, we extracted items, but what do we do now with that weird maybe type? We probably will not be able to use it with many APIs, and we need to do something about this. Fortunately, we are able to specify exactly the type that we want the flat map to be backed with. And in this case, I specify std vector. Boost flat map uses that std vector as a container that it adapts, and we can get items in the form of std vector. And of course, the opposite operation is adoption of some kind of sequence. And again, we can get items from some API or some other place. We can do something about it. And when we want to operate on those items as a map, we can pass all the elements of that collection into the map, without copying. The storage is just moved, and we can work with those items as a map with a map interface. So of course you will use auto for all the type specifiers. You don't want to spell it out explicitly, and this way you can have your map. You can do something about it using all the guarantees like unique elements and order and whatnot. You can work with it, then you can extract the sequence, you can get the items, you can, for example, pass it to some other APIs. Then maybe you can get some other form, in some other form, those items, and again, you can put those items back into the map and continue to work with the map interface. Or the other way around, you can work, you can adopt items from some other place, work with them with an interface of a map, and then extract sequence and pass it to some other parts of your code. If you don't want to pay for establishing an invariance in the adopt sequence method, you can specify order at unique range. In this case, you bear responsibility for establishing the invariance, and boost flat map kind of raises its hands and gives the wheel to you. And so we can implement the similar facilities. In this case, we have a method extract. In this case, we just move the container out. We can have adoption in the form of constructor that receives m value reference to the container. We move the container in our internal storage. Then we sort the container using predicate that we get from make predicate. Then we remove all the non-unique rather elements to the end. In this case, we use make equal to predicate using the predicate that we got specified in the template parameter. And in the end, we erase all the non-unique elements that were moved to the back of the container. So here is the make equal to predicate that uses the comparison that was given to us. And in this case, we just use equivalence expression. So if either of those keys are before the other key, then these keys are not equivalent, and we say whether these keys are equivalent or not. Again, if we don't want the user to, or rather, we want to give the ability to the user not to spend time establishing invariants, and so we can again define constant sorted unique, with which you can say that no, I don't want you, the flat map, to establish invariants. I already did all the necessary things. And so we can write code like this. We have our map. We can extract map. In this case, we get std vector, and we can put the items back in our map. And of course, you will use auto because you don't want to spell it out explicitly. And you can use sorted unique to tell that you don't want the constructor to establish invariants, that you already did this. And std flat map also has similar facilities. In this case, extract method returns a collection of containers for keys and values. And of course, you will write it probably like this. Map should be moved, probably because moved out objects requires to establish less guarantees than if this was a non-R value qualified method. So if it was if it was just regular non-const method, it had to say probably that this is the state that the initial map ends up in. But when you move from the object, you can just say that the initial map is in some valid state, but you don't want to specify in which particular state it is. So this is my guess. And you can do this like this using structured binding to get keys and values. You can move keys and values back to the map like this using constructor. Again, you can specify sorted unique to skip establishing all the invariants if you establish them yourself. And there is another method to do this using method replace. And this method imposes constraint that keys should be unique and sorted. And so I hope done with the basics, and let's see what else can we do. I would love for flat maps to be able to work with vectors of tuples, but in particular, Boost flat map can do this because Boost flat map uses explicitly first and second variables, member variables all over the code, and tuple doesn't provide first and second. In our implementation, in our basic implementation of our flat map, we can probably change the usage of first and second to get 0 and get 1. This will work both for tuples and for pairs. So I don't see that we are losing anything from that change. But there is one nuance that, for example, in this case, for subscription operator, the standard asks, or rather specifies, dictates that we need to use piecewise construct in the case of pair. Std tuple does not provide piecewise construction, and I have no recipe for this problem. We could approximate that behavior by constructing value, but that gives us unwanted temporary object that we may not want or may not be able to use because there is no default constructor, for example. Or maybe we can disable this operation altogether in the case if you use tuple. So you can use still other operations like find and insert, but you can't use subscription operator. Okay, what else can we do? It would be cool if we could specify getters and getters for key and value. So in this case, by default, we can specify that we use vector of pairs. And for key getter, we specify lambda. Please forgive me for this slide bearish presentation. This is just to take less space on the slide. Key getter in this case is lambda, generic lambda that returns the result of get 0, and value getter is generic lambda that returns the result of get 1. So basically, for pair, this is first and second, respectively. But if we want to use some different type, for example, my struct here that has key and value members, we can specify flat map like this. We have int for key, int for value. We specify comparison as std less of int. for int rather, we specify storage as a vector of my structs elements, and we specify key getter as a lambda returning reference to key, and value getter as lambda returning reference to value. So in this case, we can, throughout our implementation, theoretically use key getter and value getter to obtain keys and values from any, in general, possible type that we want to use it with. And we're coming to the end of my talk. As a conclusion, here are possible future work that I would like to see happening. Well, first and foremost, I would like to use tuples with flat maps, or maybe even arbitrary types. And for standard flat map, I would like a policy to be able to choose between single containers for elements and separate containers for keys and values. Or maybe we can use, we can have different type like zip flat map for separate containers and flat map for single container. Or maybe even we can decompose the current implementation of flat map into flat map that uses one container and zip sequence adapter that adapts two containers into one sequence that can be used by the flat map. And that's all. Thanks for listening. This is all the information you might want to get. And I want to get to question about const correctness. Yes. So let me go back to that slide. Okay. So let just a second. Let me go here. Yes. So the deal is as follows. We can define non-const version of find. And when we call that version, we know that the object, this object is not const, because otherwise, like I don't see how that would be undefined behavior to call non-const version on const object. So when we call, when someone calls find, non-const version of find, the object is non-const, should be non-const. And okay, so find, non-const find operates always on non-const object. Now, and we know the implementation of non-const find. It doesn't modify the object itself. Now, we in const version, we can just cast away const and call non-const version. And because we know the implementation, we guarantee that nothing bad will happen. If we do this the other way around, if we implement const version and do all the search and whatnot there, then we can implement non-const version as calling const version and then casting away const and returning iterator in this case, which eventually can turn into reference, and that reference will be to the element that we got through the const implementation, but cast away const. Okay. So in this case, we cannot guarantee that let me think. if in general, if that object is const, calling non-const operations can result in undefined behavior. So constness, I think I'm failing this answer, but bear with me. So if you call if the object is const, it can live in read-only data in read-only segment of memory. So if you call non-const version that gets the reference to const version, it can give you a reference to const object that can end up in read-only memory, and then you cast away const, and then you try to change that memory that is read-only memory. That will be undefined behavior. So again, if we in non-const version call the const version, generally it can give us reference to read-only memory, and then when you in non-const version cast away const, you can end up with non-const reference to read-only memory. That's undefined behavior. But the other way around, when we know that non-const implementation does not cast away const, we can and does not change the object. We can, in our const version, cast away const from this, use the non-const version, and then put const back to the reference that we eventually can get. And this way, we will never get non-const reference to read-only memory, to possibly read-only memory. I hope I explained it well enough for people maybe to try to understand. So we have another question. I'm over time. I guess we'll get the town, and I will answer all the questions there. Thank you for listening to my mumbling, and have a great rest of the conference. Goodbye.